So the setup we've got here has got a Geiger-Müller tube which detects radiation. That is then connected into the Chromebook through an interface, and that's able to count each radioactive episode, and at the moment it's counting for every 30 seconds. So at the moment you'll hear beeps. You'll hear those beeps, and that's showing that it's actually recorded a radioactive event. So we're going to leave this for about 5 minutes, and it's going to record the number of counts in 30 seconds 10 times. Then we're going to take an average of those and find out the activity of what we call background radiation. So with no radioactive sources present, we're going to find out how much radiation there is naturally in the environment, because we're going to have to discount that. We're going to have to take that background count away from all the results that we get for the radioactive sources. That's us just about to the end of the 5 minutes. And you can see that the number of counts is quite different every 30 seconds. So we're going to be able to work out an average for that background count. So the first radioactive source we're going to use is Americium 241 here, which is an alpha emitting radioactive source. So as soon as I put the source in place there, you'll see that we're getting a much higher rate there, and you can hear that on the counter, and we're going to count that over the next 30 seconds. In this clip we're going to let the time run for 30 seconds, so the software is counting all those clicks, all those beeps, all those individual radioactive episodes. But in the rest of the clips for this video, we're actually going to run time forward, and so you'll see a sort of folding transition. That means that 30 seconds has elapsed, and the count for each of these is for 30 seconds. An advantage to watching this demonstration on video is that we can move time forward. If this was being demonstrated in a classroom, there's a lot of standing around and waiting. So 4,646 counts for the alpha for that 30 seconds, 3,565 for the next 30 seconds. So you can see that that count number changes quite a bit, showing that it is quite a random event radioactivity. Sometimes you get more, sometimes you get less. I'm now going to put just a single sheet of paper in between the source and the detector. So again, keeping the distance between the source and the detector less than half a centimetre. And you can hear there has been a decrease in the number of counts from the alpha emitter, and that's because even a sheet of paper is enough to stop the relatively large alpha particles from there. If we now replace the sheet of paper with a sheet of slightly thicker card, see the effect on the count from that. Even a sheet of transparent plastic will reduce that count to 186. So the reason that the alpha source had to be so close was that when it is close we are getting a good number of counts, but when I move it away even by a centimetre of air, then we're getting a much reduced count there. So we're down there at only 115. If I extend that out to 5 centimeters, so what's happening here is the air is actually absorbing the alpha, so much reduced count there with 5 centimeters of air. Now replace the alpha source with this beta source here. This is a strontium-90 isotope, which is held in a slightly different container. When separated by a few centimeters of air, as you can hear, the beta source is giving much higher count rate. So we'll try the same tests as we had with the alpha source. We'll go straight to a bit of card, put that in the way, and measure the count rate with the beta radiation and a sheet of card there. So paper makes very little difference, the beta radiation. If we replace the paper by a thin sheet of aluminium, so a thin sheet of aluminium with beta gives us 413 counts. If we then replace that by a thicker piece of aluminium, so with the thicker aluminium you can already hear the count is reduced. So if we measure that, if we put a sheet of lead in front of the beta radiation, so lead with beta radiation, and we're getting a count of only 7, which is actually less than background, because the lead is actually preventing some of the background radiation from the environment getting to the Geiger counter. Last type of radiation is cesium-137, which is a gamma emitter. So this is gamma radiation, and pop that in there. And we'll take an initial count for gamma with no absorber. So that's gamma radiation with no absorber, and that's giving us a count of 205. Gamma with no absorber, second run, 183. And lastly, third run with gamma with no absorber, and we've got 223. So you can now take the average of those. So sheet of card in front of the gamma source. That's 189 counts with the gamma and the paper. Second run for gamma with a card absorber is 206 counts. And lastly, the third run for gamma with the card absorber, 204 counts, very similar. If we now replace the card with some aluminium, and we can now record that. So with gamma and aluminium absorber down to 170. Second run with gamma and aluminium, 221, and third run with gamma and thick aluminium, 202. So if we take the aluminium and replace it by 6.4 millimeters of lead, we'll see what effect that has on the gamma. So first run with gamma and 6 millimeters of lead was 100 counts. Second run with lead is 92 counts. So not making an appreciable difference. And with third run with lead, 83 counts. If we add in another 12 millimeters to make this nearly 2 centimeters worth of lead, and we'll see what effect that has on the gamma radiation. So with nearly 2 centimeters of lead for gamma radiation, the count has dropped down to 31 counts on the first run. 2 centimeters of lead on the second run for gamma radiation, 34 counts. And finally, third run with 2 centimeters of lead, 33 counts with gamma radiation. Obviously, if we put alpha radiation in the place of the gamma radiation, not only is the air enough to reduce the alpha, but if we leave that with 2 centimeters of lead for alpha radiation, lead, a measly 10 counts. More or less background radiation, so alpha can't get through lead either. If a high voltage supply is connected up to a gauze at the top here and a wire underneath, which you'll see in a moment, and the voltage is up at about 4000 volts. So bring the alpha source close by. You can see some sparking. Take a closer look at that down below. What's happening is the alpha particles are actually knocking electrons off the air molecules and ionizing them, causing them to be charged particles which can then carry the electricity through the air as a spark.